Here we are. This video will be chopped up once put online. Got some nice and neat stuff to start out first here. One, look for any sort of descriptors on how we should round for the test, and we want you to round 3 significant digits, probably the same for this actual test, or whatever test you're taking right now, if you're watching this in the future. Flying hover cars and all that jazz. Maybe, I don't know. So what do we have here? We have a one sample t-test. I don't know what chapter this will be in the future, but right now this is chapter 18. Identifying what chapter things are from is very important because if you need to use the formula sheet, you will need to know on chapter 18 we are doing one sample means. And there's a lot of cues in this. It says t-test and stuff like that. That's one sample means test. So going back to here, it's a test of a mean. So that's one sample means test, chapter 18. We could do confidence intervals with this and all that good stuff, but this is just a one sample test of means. Go ahead and ask the question again.
How do you know that it's chapter 18?
How do I know it's chapter 18? Because we are testing a mean, and in chapter 18, as of right now, that's just one sample t-test. So when you test a mean, all you have is one group of data, in this instance, 20 observations, for which we will hypothesize that 20 might be true. Does that make sense? I'm saying 20 might be true. And if we're saying 20 might be true, what is the symbol for the hypothesized value of the mean? The hypothesized value of the mean is what? Is what? Anyone? What is the hypothesized mean in symbol notation? If you're watching this video online, anytime there's a pause like this, try to answer it. Well, we want to do that if we do the test. We would say the null is that the true mean equals 20, but this 20 in notation is what? You can cheat and go to formula sheets and oftentimes just take a look. Close. It is the mu naught. So that's the hypothesized value of the mean right there. It's mu naught. It's basically mu. Mu is the true mean, but we're hypothesizing that the true mean is equal to 20. So it's the hypothesized value of the mean. Does that make sense to everybody? This is the hypothesized value of the mean according to the null, so it is mu naught. We have to write mu equals mu naught, so we'd write mu equals 20 for the null. So the actual estimate is 18.62, and as the problem states, the actual estimate is the sample mean. So what is the symbol for the sample mean? The symbol for the sample mean is, careful, 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 P is for proportions. The symbol for the sample mean, let's go back to our formula and cheat. When doing a t-test, the symbol for the sample mean is the what? Y bar. I'm going to keep it about this length. Y bar is the symbol for the sample mean because we have sample minus expected. We expect, according to the null, mu naught. So Y bar is the sample mean. This formula is very important right here because we're going to use it in a moment to get the t-statistic. And also, we even have the formula for the degrees of freedom. Do you notice that right there? N minus 1, which will come in use in just a moment, is the formula for the degrees of freedom. Sorry for the endless scrolling. It's just the formula page is at the end. So we have the degrees of freedom are blanked out, but let's go ahead and figure out the degrees of freedom. The degrees of freedom, as stated by the formula, it is a one sample t. The degrees of freedom is 27.
Just n minus 1.
The sample size right here, as denoted, there are 28 observations. Does that make sense? And so 28 minus 1 is 27. And the degrees of freedom for a one sample t, say it with me, the degrees of freedom for a one sample t is n minus 1. Very important, you know which degrees of freedom you're doing because it'll change from chapter to chapter. Degrees of freedom for a one sample t is n minus 1. So next we have the standard deviation. What is the notation for standard deviation? It is simply S, just S. S is the notation for standard deviation. This is going to help us find the test statistic right here. The test statistic is the t with n minus 1 degrees of freedom. So if you remember from the formula, it was y bar minus mu naught. So let's do y bar minus mu naught. Does that make sense?
Wait, so mu naught is 20?
Mu naught is 20 because that's where we're hypothesizing the mean to be.
Okay.
Y bar is 18.62. This is the difference between the two numbers. And now we are going to take and find the standard error. The standard error is, I'm taking the square root of 28. We are going to divide the standard deviation by the square root of 28. This is the standard error. So let's go down here and just look at the formula I did. This bottom part right here is the standard error. I took the standard deviation and divided by the square root of n. Does this make sense? So we take the standard deviation and divide by the square root of n. The standard deviation was, I believe, let's go back and look at it.
Is there any way you can like do this in Word too, so that we can see?
Yeah, let's do that. I like your idea because it's too much scrolling back and forth. I was feeling it too. And let's go to Insert, Equation, and let's go right here, put this in. And now, does anyone have the, what was it, 18 point, go ahead and tell me this.
2.6286 over standard deviation 2.46484 divided by the square root.
So we have y bar minus mu naught over s over square root of n. Does that make sense right there? There is our equation, and I can even one up and do better, because watch this magic. As long as everything goes the way I want it to. We go down here to the end, sorry for all the scrolling around, and I wasn't using my computer skills to the best because we have snipping tool. So let's just go ahead and take this right here and put this side by side to it. And how do you guys like this? Is that a much better way to view it? Put it in the center here. And what does this equal up to?
Negative 2.944.
Negative 2.944. That is the t-statistic.
So you can like double check this in the calculator there, right? Just to like make sure we're 100%.
You can double check this in the calculator doing t-test. T-test, because this is a t-test and it's just one sample.
X bar would just be one.
Y bar and X bar are the same thing, so this is just Y bar or X bar. That just means mean of that variable. Does this all make sense right here? Seeing it all visually now? So there we go. That is everything substituted in and all the notation. We are good.
So third part, how do you
The, which third part? Oh, the p-value?
Yeah.
Ah, that's the fun part. Because what do we have here? Let's take a look. If we go to the calculators and you don't have the David M. Lane or stat distribution calculators, you say, but Brian, we don't have these on the tests. And I understand, but look at this. Negative 2.944. And this won't give the exact, but I want us to look at something here. And let's go to the T with 27 degrees of freedom. If we were to go to negative 2.944, and if we go to the left of it, we get 0.003. If we go to the right of it, we get that. What do the less than and the greater than equal up to? Do you see that? How they equal up to 1. What happens when you take the left and the 2 tail? Now, the math is a little bit weird here because it's 0.033, and this is 0.066. It's just rounding it. What happens when you go from the left tail to the 2 tail? It what's it? Doubles it. And it is weird because we're seeing it round it because it's only doing it to 3 decimal places. But does everyone see that the 2-tailed is double the smallest? So if you take 0.033 and double it, you get 0.0066. And just in the calculator over there, it was rounding it to 0.007 because it only had it to 3 decimal places. But the 2-tailed, if you look at it again visually, is just double the smallest. Do you see that reflection appear on the other side over there? Does everyone see that on the other side? And if you don't like how the numbers are turning out, now just watch it here. There we go. Just pretend I have the right number in. Do you see how it's going from 0.003 to 0.006? Because what am I doing? I'm reflecting it on the other side. But now it's not rounding up because I pushed it further out. I made the p-value smaller. So I was just changing it there just to show the concept, proof of concept, that the two-tail is always what the smallest p-value is. Double. That is, the does not equals test always has double the smallest p-value. The smallest. Because you can't have a p-value over 1. Because I would say the probability of our results more extreme happening due to random chance variation, given that the null is true, is above 100%. So your smallest p-value could be 0 and your biggest p-value could be 1. Double your smallest is the does not equal the two-sided p-value right there. That always works for symmetric tests, which really in this class, that's all we're going to worry about. Chi-squared is a test where we're always doing does not equals. It's a little bit different of a test, and it's not a symmetric curve around 0. But when you have the t-test or a z-test, the does not equals always double the smallest. Here we go. Next question, question number 2. And online, if you have any questions, feel free to ask. You keep looking at the chat. Everyone doing all right? It is generally believed that 75% of college sophomores recycle. I have no idea why we believe that, but let's assume that is true. So are UT students, UT sophomores, different than the accepted figure? Now this right here, this different, is a very important part of the question. Because when we ask, are they different, it's automatically telling you what the alternative is going to be. Not equal to. Are UT students different? Because the null would be that they are what? The same. So we can already think of a null and alternative we could write. When you read these questions, I haven't even looked at the rest of it yet, but I can tell you what it's going to be. A researcher at UT got the cooperation of the registrar and took a sample of 128 students out of the 5,000 students. So the population size is 5,000 and their sample size is 128. How many of those students said they recycled? 84 of those students said they recycled. So with 84 students recycling, how many said they do not recycle regularly? So if 84 recycle, go ahead. 44. And those are going to be very important numbers in a moment. But let's see. Condition 1, random. So what would we write right here? We'd write in that condition 1 is random, or randomization. Then we'd circle yes, because what? It states it right here. I'd even circle that, so the greater C's. The problem says it was randomly selected. And for our tests, you need to make sure you put that it said it was random, and the problem needs to say it was random. Don't say, I assume it was random. We did that one time to people, and we took off 2 points everywhere. People were like, I assume it's random. No, 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 no. I know my Pearson questions, not fun, right? But ours will say random. Condition 2, random, and then 10%. 10% is condition number 2, which states we must sample less than 10% of the total population. What was the size of the total population here of UT sophomores? 5,000. So with 5,000 UT sophomores, we only sampled how many? So did we sample less than 10%? Yes. What would 10% of 5,000 be? 500. So we have sampled less than 10% because we've only sampled 128. Now, sometimes we don't give the population size, but let's say we had a sample of 128 and it was cars in Tennessee. Do you think we're safe then? We sample 128 cars in Tennessee to see if they meet emission standards, which is a yes-no proportion question. So I would say 128 cars is less than 10% because I assume there's more than 1,280 cars. Do you see how I figured out that number? Because if there's 1,280 cars, what's 10% of that? 128. So I believe there's more than 1,280 cars in Tennessee, so I believe we meet the 10% condition here. So 10% condition, we must sample less than 10% and show that mathematically. Always show it mathematically. 128 is less than 10%. I believe it is 2.64%. 2.66%. Use a calculator. Let's see it. I think it's 2.66. 128 divided by 5,000. And it's 2.56. My brain's a little slow today, but 2.56%. So that's way less than 10%. Condition number 3. And condition number 3, we have to see this is for making a confidence interval, which is sometimes on this test and sometimes not on this test. So let's check the condition 2 ways. If it was a confidence interval, we would need to see that what and what are greater than 10. Be careful, because this is actually not on your test. For confidence intervals, we would need to check the success failure that both what and what are greater than 10. Careful, for a confidence interval, it's NP hat and Q hat. But if it's for a test, it is what? N. Because now what do we believe is true? We believe the what is true. 4 letters, we believe the what is true in a test. The what hypothesis? The null. So you can probably tell where this question is going, that later on we would test 75%. So P naught would be 75%. Does that make sense? This is just preparation. I'm going beyond this question to show you if the question said check the conditions for doing a test, the third condition would be the success failure condition. But what math would you do? You would do N. You would times N by. You would times N by. If it's for a confidence interval, P hat. If it's for a test, P naught. Because think about it, in a test, what do we assume is true? The null. So wouldn't you do your checking of a condition based on the null? Does that make sense? So for chapter 17, when you do a test on a proportion, if the test says check the condition, the success failure condition on proportions for a test, we need to do NP naught. So let's take NP naught right here.
Wait, so is this,
Good.
is this a proportion or is this a, whatever?
This is proportions. Yeah. So we just did you see NP naught and Q naught right there?
Okay.
So this, why is this question proportions? How do we know it's proportions? How do we know this is proportions? This is a great question right here. It's percent, that's often a good clue. But I always say, go to the question we asked them. What did we ask UT students, UT sophomores? We asked them what? Do you recycle regularly? And then how would they answer that? Yes or no? Because some people might look at this and they'd say, well, it's got numbers here. It's like 84 out of 128. That's quantitative. No, no, no. The question we asked them was, do you recycle regularly? And how would they have to answer that? Yes or no? So this is the proportion of sophomores that recycle regularly. Does that make sense? So the third condition must be some form of the success failure. So since it's a success failure, if the question wanted you to do it for confidence intervals, we would have to look at NP hat and Q hat, which this one does, but on your test, we don't have confidence intervals this time around. But what is NP hat equal to? NP hat is the number of successes in the sample. How many successes were in the sample? How many failures were in the sample? And look at this. If I get P hat right here, does everyone see that this is P hat, right? Because I did successes over sample, right? And then if I times that by 128, well, didn't I just divide it by 128 to get that? So does everyone see that NP hat times N, or X over N times N equals what? X. X over N times N equals 2X. Because what is X over N? X over N is equal to P hat. But if you times that by N, you just get X. Does that make sense? NP hat, NQ hat is the number of successes in the sample and number of failures in the sample. Since this question asks us conditions for confidence intervals, we would check the NP hat and Q hat condition. If it said check them for tests, what's the third condition again? Success failure using NP naught and NQ naught, because P naught and Q naught are assumed to be true. But it's always some form of the success failure. If you have questions, feel free to ask. Go ahead. It is the success failure condition. And once again, in this context, the way it's written, we would need to check NP hat and Q hat, which is 84 and 44. Both of those are greater than or equal to 10, and we are good on both of them.
So we can just write like NP hat equals 84 and NQ hat equals
Perfect. NP hat equals 84 and Q hat equals 44. Both are greater than 10. We are good. Mathematically solve the success failure condition. Show mathematically both are greater than 10. And if it was a test, you would have to go here and say the null is 75% times the sample size of 128. And P naught is equal to 96. So then we take Q naught times 128. And NQ naught is greater than 10. Do you see how I figured those out? NP naught and NQ naught are both greater than or equal to 10. And this is just a different version of the question right here, because on your test, it could ask you to check the conditions for doing a test, not an interval. Does everyone see why I'm covering that right here?
Yeah. Can you say again?
If it was doing a test, you need to take the null proportion right here, because this is setting up for us to test 75. So that would be P naught. And then what is Q naught? It'd be 0.25, right? And then times that by n. P naught times n, Q naught times n, and then you see if there's at least 10 for each of those. Okay, so now we need to create a 93% confidence interval. Let's go ahead and work on our 93% confidence interval here by remembering our formula. So let's go ahead and grab the formula and go down here. I'm going to copy paste so we can see the formatting of it. So there's our formula, and let's go over to Word and start writing it out. Now, how did I know which formula to grab here? The formula I chose was a formula for a confidence interval for the true proportion. And what we need to start out with is our sample proportion, which was 84 over 128. That's just x over n. So I'm going to delete all this. I'm going to put in a new equation above here. So let's insert an equation. And let's go right here. And I think it does plus or minus instantaneously. Now we need the z star of 1.812. Is that correct? I don't know 93% off the top of my head that well. Now we're going to go to the square root. And we're going to put in a, right here. I love the equation builder in Word. And then we times this by Q hat. So we get 1 minus.
Wait, how did you get points? Why did you go there?
Why did I get, what is the 0.65625? Is that,
Never mind.
so to find out P hat, because I think other people might have that question too. So I don't have P hat yet. So P hat, let's do equation builder. So P hat is equal to x divided by n. And so x divided by n is merely 84 divided by 128, which is equal to 0.65625. So that's how I found P hat. And Q hat is equal to 1 minus P hat. They're complements of each other. They add up to 1. So does everyone see the work we have right here and how to obtain those answers? So this gives us our confidence interval, and we can go ahead and solve this. Does anyone have the answer right here? This is just math. Oh yeah. So the interval goes from 0.52, is it? What is it, Victoria? Let's see. Oh, the higher bound is what?
0.732319.
Cool. And actually, you know what's cool? So you've given me a problem in and of itself. Don't tell me the lower bound, because watch this. The lower bound is equal distance. This is a good practice problem right here. Because if I know the upper is that far away, we did something like this today in the office, right, Toby? So does everyone see that the upper is 0.732? How far away is that from the middle of the interval? So it's that far away. What did I just find? What did I just find by knowing how far away the upper is from the middle? I found the margin of error. So why don't I just take this number right here and subtract it from, does that make sense to everybody? Is that the right answer, Victoria? 58?
I got 58.501.
Yeah. And it's very close to this. There's just maybe some decimals. Yeah, it's just decimal differences. Anything you see right there is just little shavings. Can we use a calculator on the consoles, or we need to write out? You can use calculators as much as you want. I only care about the right answers. So if you use a calculator, I just care about the right answer. But this could be a theory question right here. We could give you part of the information and then have you find the lower bound. I was able to find it because I knew that I knew the distance from the middle of the interval to the upper has to be the same from the middle to lower. Does that make sense? So using that information right there, because this interval could simply be written out, this is just another way of writing this interval. Good practice right here. If we write out 0.65625, and I'm not in equation form anymore. Let me insert equation. 0.65625 plus or minus. Really? Well, it doesn't like me today. That was weird. Oh, I know what I'm doing. My brain is not on, guys. There we go. That is another way to write the interval, and there's a lot, I like the yeet. There's a lot of ways to write this, but these are all the same answers. Does that make sense to everybody? Good stuff. You can do the one prop z interval. One prop z interval. This in the calculator would be one prop z interval because it's with proportions. Very important right there, one prop z interval. So that is where we get our interval right here. Interpret the interval in context of the problem. I am 93% confident. Let's remove everything here. Make sure you guys have this. Please, please, please write this down. I am 93% confident that the true proportion of UT sophomores that recycle is contained in the interval 58% to 73.2%. I am 93% confident that the true proportion of UT sophomores that recycle is contained in the interval 58% to 73.2%. This is the portion right here everyone messes up. We are trying to estimate the true proportion of UT sophomores that recycle. That is what we are trying to estimate, the truth for the population. Very, very key phrasing. I am 93% confident that the true proportion of UT sophomores that recycle is contained in the interval 58% to 73.2%. So if the researcher wants to do a formal hypothesis test right here, to see if it's 75%, we need to look at the null alternative. So we would have that the null hypothesis states that the true proportion of UT sophomores that recycle is equal to 75%, where the alternative states that the true proportion of UT sophomores that recycle is what? Go ahead and tell me. 75%. This value will always be the same for both of them. This is the hypothesized true value. This is actually P naught. P naught is the hypothesized true proportion. So if we read it as a sentence that one of these things must be true. And that's the way it works with a null and alternative. One of these things, and we can do a one-side alternative, but with the two-side alternative, one of them must be true. They can't both be true. So when we look at this right here, the null states that the true proportion of UT sophomores that recycle is equal to 75%, where the alternative states that the true proportion of UT sophomores that recycle is not equal to 75%.
So it's just, it's not like
the first one right here is a population parameter. This symbol right here is always a population parameter, or it could be the difference between two means, difference between two proportions. But when we use this symbol right here, it's a population parameter. This right here, and this is not the answer to the question, but this in notation form is P naught. Does that make sense? Because that is the hypothesized true proportion. So just in notation, 75% is P naught, because we're saying The true proportion is what we hypothesize it to be according to the null. Does that make sense? So the true proportion is the hypothesized proportion, which is 75%. And that's what we hypothesize it to be. And then the alternative would be that it is not equal to that. What did you notice about our interval? Go back in time right here. What did you notice about this interval we created? You're exactly right. The interval we created right here does not contain 75%. So that is a big, big thing for us right here. The interval does not contain 75%. So when we do this right here, and as you see with this interval too, knowing that our interval does not contain 75%, what would you do to 75%? Continue to believe it? You would reject it. And failing to reject the null means you continue to believe it. It sounds weird to say fail to reject, but you could just say, I do not reject the null. Does that sound easier? I do not reject. That is what fail to reject means, is I did not reject the null. So you would either reject the null or not reject the null. You don't accept it. You just continue to believe it. You're like, I continue to believe it. But in this instance, since 75 is not in our interval, we reject it. And that's the whole reason. Because anything outside the interval does not seem plausible. Interpreting this interval, I am 93% confident, this is not the right interval, but it's if you didn't have an answer, that the true proportion of UT sophomores that recycle is contained in the interval 23.4% to 67.8%. Thus, 75% does not seem plausible. So I am going to what 75%? Reject it. So we can reject 75%. Now, anytime we do a test with a confidence interval, it will have an associated alpha level. So going over here, let's take a look at it. When we do we can look at the alpha level. The alpha level equals, that's all it is. So when you look at this right here, if you have area inside, the area outside adds up to 1. Does that make sense? Like when we used to do 95% inside, what was total outside? 5%. So if you make a 95% confidence interval, what's the associated alpha level? 95% confidence interval, the associated alpha level is 5%. 93% confidence interval, the associated alpha level on the two-tailed test is 7%. Does that make sense? Because if there's 95 inside, what's outside? If there's 93 inside, what's outside? 7. And it's a two-tailed test because you talk about outside total. So this is the associated alpha level right here. And whoops, let me change this, 2 seconds. There it is right there. So it is 7% or 0.07, whichever way you like to say it. We would accept either one, no worries. Okay. Here we are to another question. In this question right here, we are doing what? And it starts out with this. We have British men and we have USA men. And we think that who might be taller? Sorry, British men. We think USA men. A researcher believes that British men are shorter on average, which means that men in the United States are taller, is like what they believe. Doesn't mean they are, it's just what they believe at the moment. So think about this, how would we collect data from this? If you said, I don't believe that, how would you collect data? And that's what we do here. How would you collect data? You would take a sample of men from where? Britain, and you would take a sample of men from where? How many samples do you have? 2. Are the samples independent of each other? Because it's like, will men's height in Britain affect men's heights in the United States? Like a guy's like, oh, that guy in Britain's really tall, I'm going to boost up. No, it doesn't affect the heights of people in other countries. So what do we see? We have 2 independent means. This is at the moment, chapter 20, 2 independent means. Very important to know. That's going to help us with the formulas here in a moment if we have to use any. Write down the null and the alternative suggested by the problem. And once again, we are suggesting that British men are shorter than American men. So here we are with a null and alternative. And let's go ahead and write HA. Get our null started up here. And this one's a little bit more tricky. Sorry, because we need to incorporate some symbols right here. Let's go over to our symbols and hope they're on here. There it is. We have mu USA minus mu of Britain. Is that right? equals to what? Because what would the null state about the difference of heights between the two countries? There's no difference. Because what would they need? They would need evidence to suggest. Now I want you to think about something here. When we do the alternative right here, click the wrong button. When we do the alternative right here, if we want to say that many in the United States are taller, if we do 10 minus 8, because you see how 10 minus 8, would that be a positive or negative number? Positive, so what sign should I put here? Does that make sense? That's the way I figure it out in my head every time. I'm always like, okay, wait, if many United States are taller, then this should be greater than 0. You can also take this symbol and put it in between here. That's another way, if you just want to do it quickly, put this symbol in between, and you could actually rewrite it like that. Some people don't like to do it. We've had qualms about it, but frankly, that's the same thing, right? Does that make sense? Question, go ahead.
Are there any tips to remember if you should put USA or Brighton?
There is great question, great question. So the question was, knowing which way to put them. Go down here to the output, and the output should do it. And also with the output, sorry online people, you won't be able to see this, but you could literally just write mu and mu before these, and you basically have it. And if you see this kind of output right here, you have two independent means. That's the only way this output shows up, is when we have two independent means. Great question. So knowing the order, look at the output, and I kind of knew the order already. And USA always comes first, everyone knows that. So why it's 0? Because we want to see if British men are shorter. So we'd assume that there is no difference to begin, and then we'd see if there's evidence that they're shorter, which also implies American men are taller. So 0 implies that there is no difference between the average heights of USA men, and this is the true average height according to the population of USA men and the population of British men. There's no difference between their average heights, and then this one implies USA men are taller, also implies British men are shorter on average. Does that make sense? Chapter 22, problem. Did you have another question, Victoria, or a little clarification? Okay.
Chapter 20 or chapter
20, excuse me. Good catch. Below is the output. And oh, I love this question. I love this question so much because it's so easy, yet it seems so difficult. When we go down here to the equation, anytime we do a test, a test is always a difference. What? I was about to say it, but I want you guys to tell me. Well, a test is always we take a difference and then we what that difference? Standardize it. So do you see the difference right here in this equation? The difference between the two means. And this 0 is superfluous. It does nothing. It's a delta in some equations. In other classes, you'll learn about that. But the difference, and then we standardize it. Does that make sense? A test is a difference standardized. And you can see that in the other ones. Look, a difference standardized. A difference standardized. This one's a little bit different, but it's still like a difference between those standardized by that. Does that make sense? We're just taking differences and standardizing them when we do tests. So let's look at our output now and see if we see something that sounds like a difference standardized. Does everyone see that? The standard error of the differences is what we're dividing by. The standard error of the differences is literally this whole formula right here. This whole thing is called the standard error of the differences. So you could go through and you could work this problem by finding that value by taking all these standard deviations, all these sample sizes. But I want you to see in this output right here, all I'm going to do is divide those two numbers. If you take 3.49714 and divide by 1.33411, I'm taking the difference between these two means and whatting it? Standardizing it, and there is my test statistic. And look, does that look to be about 2.6 in terms of t-scores, like 2.6 away? Now don't look at the number line down here because that's not t-scores. But you know, like 1, 2, 3 when we go out on the normal curve, you guys remember that? Does that look to be about 2.6 in between 2 and 3 if this had normal curve numbers below it? Yeah, because like 1 would be about here, 2, 3. You guys get what I'm saying? If it had z-scores or t-scores on it, it'd be like 1, 2, 3 going out. And you can see, you could take a guesstimate and say, that looks to be about a t-score of, I don't know, 2 or 3. And what do you get? 2 or 3. So what does this t-score mean? Here's what you can't do on the test, is you can't go to the applet right here and plug in 67 degrees of freedom, which is just an estimate of our degrees of freedom, plug in the t, and then get the p-values of like 0.0005. Does everyone see that exact same p-value and the same graphic? Does that make sense to everybody? You can't do that. But you can see how the output relates. You can see here what we're obtaining by plugging in the t-ratio. The t-ratio is going to get you the p-values. We simply go and find the p-values based on left tail, right tail, or two tail, which are all being shown in the output below, and just follow the same relationship of the does not equals is double the smallest, and the less than and greater than equal up to what? They equal up to 1. They equal up to 1. What do you notice is not inside this interval right here for the difference? When we say I am 95% confident the true difference is contained in the interval blank to blank, 0 is not contained in the interval. So if we did USA minus Britain, which of the two was taller if the difference comes out positive? The difference came out positive, which of the two was taller? USA. And since the confidence interval is positive, do you think that means we have evidence that USA men were taller? Yeah, because I think the true difference right here is contained in the interval 0.83 inches to 6.15 inches, showing that USA men are generally taller than British men by this amount. And what do you notice we do with the alternative here? We what the null? We reject. And we'll look at the alpha level here in a moment, but that's a very small p-value. How do I know this is the alternative? Do you see how it has the greater than sign? Put that greater than symbol right here. Just move the greater than symbol into there. This would be a does not equal symbol if you use this one because it's an absolute value, and this would be the less than. Do we have evidence that USA men are shorter than British men? Could we reject the null and show evidence for that? No. Look at the p-value. There's no evidence that British men are taller than American men. But there is evidence that who is taller? That USA men are taller. So that is the p-value we have to circle right here, the one related to the greater than alternative. Simply take the greater than and plug it in right in here. Just put the greater than symbol right there.
Can you say again what,
So, go ahead.
what you got the missing value was on the t-ratio?
The missing value on the t-ratio was 2.621. And the key is, I'll answer all questions. The key is online if you missed something. So yeah, there is the key too. But I divided the difference by the standard error of the differences, which is using this formula right here.
And so then the one that would be circled would be there's a
The one you would circle would be the answer right here. And we will go a little bit over today because I'll keep recording. You guys can stay or leave at any point. I'll keep going. I'll probably go to 6:30 or so because we'll try to get through the whole thing. So what would we do right here at the 0.001 level? Look at your p-value, and at the 0.001 level, what would we do? Very specific 0.01 level. Can we reject the null or fail to reject? And why do we reject the null? Because the p-value is what to alpha? Very important. When the p-value is less than alpha, we reject the null. We're saying our results are unlikely to happen by random chance. We reject the null. If anyone online has any questions, feel free to ask. But our p-value was less than the alpha. If the question doesn't give alpha, assume 0.05. So state the remainder of your conclusion. And here's the big thing. This is where people make mistakes. If we go back in time, I'm going to read off my conclusion to you. When you reject the null, simply follow the following format. I reject the null that the difference between the true heights of USA men and Britain heights is equal to 0. Does everyone see how I read that? I have evidence for the alternative that the difference between USA men and Britain's height is greater than 0, implying that USA men are probably taller than British men. I had a little addendum sentence on there to make it clear, but all I had to say was, I reject the null that, and then I just read it. If you write these out properly, you can then just say, I reject this. I have evidence of this. That's all you have to do is state it in context. Just make sure to say it in context when you write a sentence. I reject the null that the true difference between USA heights and Britain heights of men is equal to 0. I have evidence for the alternative that the true mean heights, the difference between the true mean heights of USA and British men is greater than 0, implying that USA men are taller on average. Because that's what we saw, said USA men were taller. We had evidence of that. If we failed to reject, we could probably just say, literally we could have said this, because we failed to reject. And that frankly would be enough. I continue to believe the null that the true mean, there is no difference between the true mean heights of USA men and British men. So you're just saying you continue, because you didn't reject it. I failed to reject. We didn't do that in this problem, but if we did fail to reject, you could just say I continue to believe the null. And then you could probably just say, I wouldn't count off points if I was the grader, there was not enough evidence for the alternative. And I wouldn't need you to get wordy on it. It's just, we continue to believe that there is no difference between the true mean heights of British men and USA men. Does that make sense? And then you could leave it at that. But once again, in our problem, we did have evidence. So I rejected that and I had evidence for that.
So we can just write that.
Yeah, make sure to put it in sentence, read it out. I reject the null that the true difference between USA men and British heights is equal to 0. Just write that as a sentence. You see, I'm just reading this. The null that the true difference between USA and British heights is equal to 0. So make sure to write it as a sentence. But all you have to do is just say, I reject, I have evidence, and then read your null and alternative as a sentence. But just make sure how to read them. Make sure to know that notation. Question number 4. 25 minutes left. The following is some output from JUMP for a 1-sample t-test with a 95% confidence interval. This question is short and sweet, and I like it because there's really a quick way of doing this question, and it's just hammering down a topic we've already done. Looking at this output right here, we're given a lot of p-values, but we want to look at the p-value for the does not equals test here. Does that make sense? The does not equals test can also be done by doing a what? Confidence interval. So let's go over here and look at the confidence interval. What value were we testing over here? 22. According to your confidence interval, can you reject or fail to reject 22? You can reject it. And at what alpha level would you reject it on a two-tailed test? 5%. Does everyone see how Victoria found 5%? Because it's a 95% confidence interval. Does that make sense? Since we built a 95% confidence interval, we can reject at the 5% level. And what is the only p-value over here that allows you to reject at the 5% level? Does that make sense? Questions? Go ahead. It was short and sweet, but I want to make sure we made it clear.
So how is it D the answer?
How is D not the answer?
Yeah.
Can D be rejected? Is D something we would reject with an alpha of 0.05? No, because it's not below 0.05. Since 22 is not in the interval, we would reject 22 at the 0.05 level. Does that make sense? Because why did I say 0.05? Because what kind of confidence interval is this? 95. So it's analogous to doing a test with a 0.05 alpha. Anything tested, we could test at the 0.05 level by saying, is it in or out of the interval? So this specifically is the does not equals test because it is the absolute value. So testing and confidence intervals are the same thing. I've highlighted both right here, the confidence interval and the test, and anything tested that is outside the interval would be rejected at the 0.05 level on the two-tailed test. Specifically, this one right here for jump output, the absolute value, because that's either side, two-tailed.
So we'd be given one that's like that. Like
Well, you might not even be given something like this. This is just we already did something like this by looking at an interval earlier when we did the proportion of UT sophomores. Remember that one? So that one we tested 75 by seeing if it was in or out of the interval. So this test has had a lot of using an interval to do a test. Not saying any test in the future will, or your test, or who knows. Always be careful. Sometimes people overstudy the practice test. So you might not be given anything like this. I don't know. Never know, Victoria. Never know. I don't know. We don't have the test done yet. And the test is a week from today. We don't have the test completed yet. We're still, I don't know, maybe Charlie's already completed it, but I have not seen the test. So I can literally say I do not know. I would suspect you won't have a question almost similar to, I mean, I think there will be the concept of using a confidence interval to do a test, but it might not be perfectly analogous. So it's always hard. There's always newish questions. There's always oldish questions. And be careful if you ever look at way old tests, because the information, sometimes we change like what we cover. So watch out. You might be like, I have people bring stuff to StatLab and be like, I don't understand. I don't remember this. I'm like, yeah, because we never did it. Like you don't need the binomial model. So, okay. So classic question right here. So in this one, suppose the business analytics department comes up with some method of determining whether students cheat or they did not cheat on a test. What is the fairest thing to assume about a student cheating on a test? Should we start out saying they're all cheaters? We should start with the null because we assume the null until we have evidence for the alternative, and the null should be that the student what? Did not cheat. Now, when we make a type 1 error, what do we do to the null? And actually, I think we came up with a way of doing this. In a type 1 error, the null is what? Do you see how I have a 1 on top of here? This is my new way of teaching it. I'm pioneering it on you guys. You guys tell me if you like it or don't. In a type 1 error, the null is what? No, just go with this. In a type 1 error, the null is true. So if we make an error, what would we do to a true null? We would what it? Reject it. In a type 2 error, the null is what? Do you see the F? Do you guys like this new way? It's my new way. The null is false. But if we make an error, this is the actual truth right here. In a type 1 error, type 1, the null is what? True, and what did we do to it? Rejected it. In a type 2 error, the null is what? And what did we do? Failed to reject it, because we're going to make an error here. Does everyone understand that? This is my new way. I like it. Students are like, we did it in the office a little bit. They're like, oh, that's really good. Type 1, type 2. Because true, false. The null is true, the null is false. So just remember, you make an error. You have to understand what it means to make an error. So if the null is true in a type 1 and we reject it, what did we say about the student? They cheated. What do you guys think about this new way? Much better? In a type 1 error, you like it? Yeah. Cool. Good. Thanks, Joey. In a type 1 error, we reject a true null because the null is true and we reject it. So now look up there at the things where it says the student did not cheat. What are we going to do to that in a type 1 error? Reject it, but is the null true? In a type 1 error, the null is true. See, I got it right here. The null is true, but we rejected it. So tell me about that student. Did they cheat?
No, didn't cheat.
They didn't cheat, but we're saying they did cheat. In a type 2 error, the null is false. So tell me, did that student cheat? Yes, they did. The null is false. But what do we believe? They didn't cheat. It's always the opposite. What we believe is always the opposite of the truth in any of these. The null is true in a type 1. The null is false in a type 2. 1, 2. That's all you got to do right there. Null is true. Null is false. So right here, we have, and I like this new method. I'm going to show it to Charlie, see what he thinks. So in a type 2 error, we say that the null is false. So what we are going to say, since we make an error, is we are not going to find it false. So we're going to say they didn't cheat when they actually did cheat. So tell me, if you had to pick one of these two situations to be in, I'll understand. What situation would you prefer? Type 2 error. So type 1 would be worse. There's a lot of ways to phrase this question, but a type 1 would be worse because you didn't cheat and they say that you did. And in type 2, you did cheat and they say you didn't. So from a lot of students' perspective, they'd rather cheat and not get caught than not cheat and get caught for cheating. Does that make sense? So, but by a teacher's perspective, a teacher could say, like, I don't care. I don't care if I haul students into my office and tell them they cheated and they didn't. I'll let judicial sort that out. I'd rather catch all the cheaters. So it's not that one error is always worse. It's perspective. It's all about perspective with these errors when we have false positives and false negatives. So what is the probability of making a type 2 error? 1, 2, A, B. Type 2 is beta. The probability of making a type 2 error is beta, and this is power over right here. Power is being able to correctly reject a false null. So this is power, and this is beta. and increasing alpha increases type 1. Chi-squared test and 1 minus alpha are nothing. 1 minus alpha actually finds you the related confidence interval level for a two-tailed test with alpha. So that's really the only time you use 1 minus alpha to find the related confidence interval. But the answer for this one is beta. Beta is the probability of a type 2 error. 1 minus beta is power. So we are looking at an emergency room right here, and they're trying to see if they can get people to take the initial survey in 2 minutes. And they want to see if it takes longer than 2 minutes. So how long it takes to get the questions. I think they're trying to do, the emergency room believes that the average amount of time it takes to get these answered questions is 2 minutes. Most emergency room employees believe it takes longer than that on average. So the manager says it's 2 minutes, but the people in the emergency room, the employees, say it takes longer. What does this sound like to you? We're going to do? Just look at the first question. We're going to test the mean. So here we are with our data. So if we collect data from how long it takes for each person in the emergency room to do this initial survey, what kind of data are we collecting? Quantitative data. So we're testing a mean. So let's go over here to our null and alternative and change what we have written. So now we are just testing a single mean. And what is the hypothesized value we are testing against? 2 minutes. So we are saying that the null states that the true mean time it takes to fill out the survey is equal to 2 minutes. The alternative is that the true mean time it takes is more than 2 minutes. Does that make sense? We're right about to hit time. You're free to go at any time, but I will continue on. You're obviously not penalized if you leave, but I'll continue on here and we'll try to get through a bit more of this. So the null and alternative is that the true mean time it takes is 2 minutes. The alternative states that the true mean times it takes is longer than 2 minutes. Below is some output. Interesting thing about this output. Our 3 conditions are random, 10%, and the third condition is what here? The nearly normal. Looking at this data right here with the nearly normal condition, does that look pretty normal? Yeah. And now if we were to do the distribution of means of sample size 32, that would be even more normal. So it gets more normal when you have a larger sample size, the distribution of means of sample size 32. I'm using the large enough n to say, well, if this looks pretty normal, the distribution of means of sample size 32 would be even more normal. It definitely passes the nearly normal condition via the large enough n kind of aspect of the nearly normal. We could also check this condition using p-values using a goodness of fit test. Had I ran a goodness of fit test on this, you would see, let's look at goodness of fit output and jump. If you were to see a goodness of fit test, hey, it's my video. They're doing a different distribution over here. This one would fail the goodness of fit test right here. This is a goodness of fit test to see if the normal is a good fit. And this one, although it looks good, would fail the goodness of fit, but would it pass the nearly normal? It would, because look at the sample size. Do you see how this is only a little bit skewed? The sample size here is at least what? 25.
Oh, it's 25.
If it's skewed, and then it needs to be 100 if it's really skewed. Does that make sense to everybody? So it failed the goodness of fit. So we can't say it's normal because of the goodness of fit, but the sample size here is very large, and that's the large enough n. So we could have used a goodness of fit. If it passes the goodness of fit, look at it. The null is that the data is from the normal, but I reject the null. This is a review from chapter 5.
Why are we going to do really normal again for this problem?
Because we're going to put a normal distribution on it. We're going to use kind of an aspect of the normal. Well, the reason it's nearly normal explicitly is because it's quantitative data. How long were you in the emergency room for is a quantitative question. So since it's quantitative, it's nearly normal. Quantitative data is the nearly normal condition. Good question. Calculate the value of the test statistic for the hypothesis test. Oh, this is so nice. Look at this right here. Does everyone see mean, standard deviation, and then what's below standard deviation? Standard error of the mean. The standard error of the mean is simply calculated by taking the standard deviation and dividing it by the square root of n. The square root of n being 32, if we take 0.33824 divided by the square root of n, we get the standard error of the mean. That's that s over square root of n is the standard error of the mean. So all we need to do here, let's go back and do formulas now. So when we take this, so let's go ahead right here and take our formula. And insert equation. And there we go. Okay, so now we need to take the sample mean. So we need to take our sample mean of 2.24 minus our hypothesized mean, and then do s over square root of n, but I showed that that is just the standard error of the mean, which is 0.0597. And so let's take these numbers right here, 2.24 minus 2, and then divide that by 0.0597, and we get about 4. And that was a little bit of rough rounding. Does anyone have the exact value for the test? I got 4.02 with a little bit of rough rounding. Oh, it's 4.02? Oh, good. So we calculated the test statistic right there. And now I want us to think for a second. Because based on our answer, would we reject the null or fail to reject the null? Is a t of 4 very large? Yes. Think about your z's, 68, 95, 99.7. So is a t of 4 very large?
I think so.
You're right. That is very large. We can go over here and we can view it. This, I believe, had a sample of 32. I know you can't do this on the test, but just think about it for a moment. At 31 degrees of freedom, it kind of looks like the normal, right? And we're doing a greater than test. So let's do a right tail. What's that p-value? So always do a drawing here. Remember, after so many degrees of freedom, the t is just like the normal. If I told you the z-score was 4, would you say that was a large z-score? And what's the area above 4? It's very close to what? Look at the graphic. Very close to 0. Because 68, 95, 99.7 above 3 is only 0.0015. So we could show that right here if we did the normal, but this is kind of like the normal. It's not the normal. It's a t with 31 degrees of freedom. So we would reject the null definitely. And what would we say for our hypothesis test? This is the last part here before we get to question 7. We'll end on this right here. So what would we say? Once again, let's go back here. And the way we do our hypothesis test is nice and simple when we state our conclusion. I reject, I have evidence. So let's read it. I reject the null that the true mean wait time in the emergency room is equal to 2 minutes. I have evidence for the alternative that the true mean wait time in the emergency room is greater than 2 minutes. All you have to do to state in context. I love these in context questions. You just have to state, I reject, and then say your null. I have evidence, say your alternative. But then if we did not, I like that a lot. I like that I continue to believe. It doesn't mean it's true. It's just like, I continue to believe this. This is what I currently believe. I did not reject this. You could say I do not reject the null. I did not reject the null, but I continue to believe. Like we continue to believe after doing this study that the average wait time was 2 minutes. Does that make sense? Would you understand that? But we collected a bunch of data and we continue to believe it is 2 minutes. We did not have evidence against that. So you could say there was not evidence for an alternative. Let's start back up on number 7. And here we are with some jump output. And I just did this one for the video, so let's see what we have. We have the upper and the lower confidence limit on this interval. And that is given to us right here and right here. Now, what I would do is interpret this interval, because you never know what's going to be asked on the test. So it's always good to just go and interpret it. So I am, and let's say it right here, I am 95% confident that the true difference between group 1 and group 2, right there, is contained in the interval negative 1.4648 to negative 7.3752. And now an important question right here that we sometimes ask, which group had the higher mean? So can you tell me, we only have one person in the class right now, I think, but which group had the higher mean? So which group had the higher mean? Let's see. You are correct. It is group 1. Group 1 had the higher mean. And how do we know that? I always do a kind of simple math equation here where I just ask myself, what is 4 minus 8? 4 minus 8 would be about -4. You see how this difference we observe right here is the difference between the two groups? So if the difference is negative, the second one has to be bigger because 4 minus 8 is -4. And I know that's not the exact numbers, but it's how I keep it straight in my head to be like, okay, 4 minus 8 is about -4. So the group 1 had to be bigger. It's the second one, but it's group 1. And that's the way I double check. And we've literally asked, what does this difference mean? This difference in context of the problem right here is that group 1's mean was 4.42 higher. So a question on the test could say, interpret the difference. A good interpretation of that difference is group 1 had a sample mean that was 4.42 higher than group 2. So now let's go to the actual question. Enough of me making up questions. The actual question here says, what is the margin of error of this interval? And when we think about this, I'm going to do a little rounding here. But let's bring this down. You might have someone else just join. And let's see. At the lower portion of the interval, we have -7.3752. And then at the middle of the interval, we have -4.42. Then at the upper portion of the interval, we have -1.4648. So the margin of error is literally the distance from the upper to the lower, and actually upper is the upper to the middle, or it could be described as the middle to the lower because this is the plus or minus. You have to go up or down this amount right there. So that is the margin of error. And we can figure it out just by taking the difference between those numbers. You could also take the difference between the two numbers. And what if we took the upper and the lower and found their difference? What could we do to get the margin of error from this? How could we find the margin of error? And hint, I'm kind of telling you right now, we could do what if we took the difference between the upper and the lower? The margin of error is always half the length of the interval. Nice job, Mallory. It's half the length. So there's a lot of ways to answer this question because there's a lot of ways we could ask it. So watch out. We've asked this one in tricky ways in the past. And just to confirm, if we take the upper, and as long as we just get the difference between the two numbers and divide by 2, you get the margin of error. And if we take the difference between other numbers, I know I'm using the positive, but it still works. And we get the same answer there. Or we could take 4.42 and subtract 1.4648, and we get the margin of error there. And you could confirm this by adding and subtracting. Let's go right here, and we could confirm our answer by going negative 4.42 and then plus or minus 2.9552. And this would confirm our answer right here. So if we add to this, oops, let's go back to our calculator. If we add, I guess I could do the negative, well, 4.42, we get that. And you can see just with the negatives or positives, you would get the right answers. To show it exactly, if we put 4.42 and do negative, and then add to that 2.9552, we do get the answer right there. So that's using the actual numbers, but it shows that we just go plus or minus the margin of error, and that is your confidence interval. The difference is at the center of it, and then plus or minus the margin of error. If you have any questions, feel free to ask. Wait, so on the test, you could put the negative or positive and be correct. The margin of error is just a number. It actually isn't really negative or positive because it's literally just this number. You would add and subtract a margin of error. And I was just showing mathematically that you can add or subtract this number to get these two. You can add or subtract the margin of error from the difference and get that. But the margin of error would simply be just a number. It's not either positive or negative because it's both. So good question right there. On the test, I would just put a number, and it's not positive or negative. It's just the margin of error is this because it's a plus or minus. So in truth, if you were to be exact, you could say the margin of error is plus or minus this amount. So Great questions, great questions. Just a little me going verbose on the explanations. This question. We're going to go ahead and go down here and grab a formula to help us explain this question. This was one of the longer ones on the video, and this video is now up. Have you checked out any of the new videos, Mallory? What do you think of the new videos? Are they good, bad, horrible? Maybe I don't know if you've even checked them out yet. We'll see. We need to grab this one right here because we're doing the difference between two sample means. So let's go back up now. And here we are. So this is the difference between two means. And so now we have the t, and this long part right here seems like a lot. Everything inside of here where it says standard error. So this is the standard error of the differences. This whole portion right in here is the standard error of the differences. And luckily for us, if we go back up, we have the standard error of the differences. That's key to this problem, is identifying that the standard error of the differences given right here is the standard error of the differences right here. And if you know that, all we're going to do is take and plug in the standard error of the differences, which is 1.4713, and then it becomes an algebra problem. Because what is this going to equal right here? The formula, are you seeing right here, this part, so ask questions if you have, how did I even know to use that formula? Good question. How did I know to use this formula? Let's take a look at the question. In this question, we are doing a t-test. We see that first. This narrows it down to 2 chapters for us. Since it's a t-test, it's obviously a chapter dealing with what kind of data? What kind of data is this dealing with if it's a t-test? It is dealing with, I'll say in a second, I think Mallory knows though. It is dealing with quantitative data. So it's dealing with quantitative data if it's a t-test, because Mr. T is mean, and if it's means, it's the t-test. But then we need to know, is it a single mean or 2 means? And so what do you see right here? 1 mean or 2 means? We see 2 means. So now we know that we need to do with 2 means. So going down here, we are only limited to a few formulas. Going down here to our formula sheet, we have the formula for, and I wish I could highlight, maybe I can highlight somehow. We have the highlight for doing a test, and we have the highlight for the interval. So we actually have the difference between the 2 sample means, that's the difference, and we have the standard error. And take a look at this. That means we can solve this whole equation right here, but we don't know t. If we just have one unknown, we can then find that unknown in the equation. So when we solve this, if we take this interval right here and we do minus, we will get the lower bound. Because now we're going to subtract the margin of error, which this is the margin of error because we have here our interval. Let me reduce this down a little bit. Let me raise this up. Here's the formula on the screen with the formula written out. Oh, it's also there. Brain's not on today. So let's go back to it and talk about it with it on the screen. Here we are. So there's the formula right here. That's how I found it. And then I know that if I subtract the margin of error, I will get the lower bound. Going back to what we have in the problem, the lower bound is going to be negative 7.3752. So the lower bound right here is negative 7.3752. So now it literally becomes solving for the t. This is all it is. Let's take and we want to add to both sides this 4.42 because it's negative, so we're going to add it. So when we take negative 7.3752 and negative, so then we're going to add to it 4.42, and we get this answer, which that is that is the margin of error. And take a look at that right there. Does that make sense now that the margin of error is 2.9552, but now look at this. What do we need to times t by to get the margin of error. And we times it by the standard error. Look at that. We have the standard error and we have t. So I guess you could have actually gone to this step. This is another way of solving right here, is just to say, well, I know that the margin of error equals this, so here we are. So we've gone through there, and now all we do is just solve the algebra. We divide by 1.44713, and we get our answers as follows. And that's what t equals. So t equals, there we go. And does that make sense right there? It's just a big algebra problem that we have to do, and that would round. T can be plus or minus because you're going to use it as a plus or minus in this formula. It doesn't matter if you do minus t, because everything here is plus or minus. I think a lot of people really fret about these problems. These problems are highly missed problems because they're more of an algebra problem. And if you don't pick the right formula, don't solve it correctly, people get it wrong. Don't let this problem be the problem you spend 2 hours working on, because we always find some way to ask some question that's kind of like this, but I feel like this is the question on the test. These questions on the practice test, people really spend like 4 hours like practicing. But if you want to practice one like it, this is my Brian suggestion for you, I'd go back to another one with a confidence interval. And so let's go to this confidence interval right here. And with this confidence interval right here, see if you could find the t statistic for it. And you could go back, because you have the standard error, you're basically given the same information. So you could go back through and see if it works. And so the biggest thing, as said, is knowing which formulas to use. If we were to back solve this one, I tell you what, we don't have that much left more on this, so let's do a big explanation here and pick the right formula for this one and find out the t statistic on this question. So on this question right here, we're going to find the t statistic just like we did on the previous one. So we're just making up a new question right here. So Mallory, let's see. Since this is means, and I see t's down here, what are we doing? Well, since it's means, we're doing quantitative, right? But do you see two means or one mean? Do you see two or one mean? Two or one, we just see one. So now when we go to the formulas, because the biggest thing is knowing what formulas to use, if we're doing the confidence intervals, do you see the right confidence interval formula when we have one mean? So I want to find the t statistic for this, and here's the one I'm going to use because it's a confidence interval for a single mean. So there was only one mean, and it's a t-test, and you see the t's there. Just match up the output. There's one mean, and we're doing the confidence interval. So let's go ahead and take this right here, and this is just another example. This is not a question on the test, but we're just finding the t statistic used in this question. So let's go all the way back up right here, and we went to the new one. We're just making up a fake question. Here we are, and let's figure it out. So here's our formula, and let's plug in our values. This is the sample mean. So if I plug in the sample mean right here, I need to plug in the sample mean of 24.0303, and then I'm going to go plus or minus the t statistic we do not know, and then I am given the standard error. And if I subtract, here's a key question, if I subtract the margin of error from the center of the interval, what will I find, Mallory? What will this equal? If I subtract it'll equal the lower bound, exactly. And that's what we did last time, is so if we take the center of the interval minus the margin of error, because everything here is the margin of error, this is the standard error, just that solves to what is called the standard error, we will get the lower bound. So let's go ahead and input the lower bound right here of 22.797246. And now let's take and get the difference. We need to subtract 24. All I'm doing is the algebra now. And we get that right there. So I just subtracted this from both sides. And actually this comes out negative, does it? Truthfully, it doesn't matter if it's negative or positive because the t statistic is a plus or minus. So don't worry, once you get to this part, all we have to do now is divide by. All I'm going to do is divide this number by this. And it's funny enough, I want to point this out. we get something very close to 2 again. So the t here, once we divide, all we're doing is dividing, doing algebra. And we can just give the absolute value of the t. So this is the t statistic now, and it is very close to 2. Because 68, 95, 99.7, your t statistic, when you have enough degrees of freedom, which, do we have a sample size on here? The sample size is 33. The more degrees of freedom you have, the more the t is like the z. Yes, I'm glad to hear that. Mallory says makes more sense now. I like that. So your t, especially if you have a lot of degrees of freedom, Mallory, if I had 1,000 degrees of freedom, what would the t basically be for a 95% confidence interval? For a 95% confidence interval with tons of freedom, it would basically be what? I'll accept 2 answers here. Hint, hint, hint. 2. 2 is a good answer. 1.96 more specifically, but 2 is close enough. It's kind of just like 2, which is our 68, 95, 99.7. The less freedom it has, the more it's pressed down, and it'll be bigger than 2. So if you only had like 10 degrees of freedom, your t's more pressed out, and it's bigger than 2. So it gets more pressed down. Great questions. Good stuff. I'm glad you're here, Mallory. It'd be so weird if no one was here. I'd be like, so that's a question. But you're helping out a lot with all the questions, so we can even do newish stuff. Let's see. That's the end of that question. Now we get to the big one. And this is the one I'm currently editing. It's consuming my life. But let's write out the null and the alternative. And I've got some really cool editing stuff when I've got this one going on, because this one changes the name of the game. Automatically, when you see a contingency table, anytime you see a contingency table or a mosaic plot, and there's another contingency table, and here's a mosaic plot, you should know we are doing the what? If we see a contingency table and a mosaic plot, it's most likely that we are doing the, it's been on the screen here a little bit, it's on screen now, we are doing the chi-squared test of independence. We are doing the chi-squared test of independence. And the only way you get, yeah, there you go. The only way you get a contingency table is when you have categorical data. And think about it. Age groups puts people into categories. Now I know age is quantitative, but age group is a category. Political party puts people into categories. And you literally, this is count data, which is one of our conditions. There are 131 Democrats who are 18 to 29. We could count them. We could say 1, 2, 3, 4. And this isn't a quantitative amount. We didn't ask them, you know, oh, that's all right. We're doing tons of questions here, and this will be posted up soon, Brooke. So this is count data because it's categorical. And if we are doing the chi-squared test of independence, this is the one chapter in which you can do the null alternative just by writing it. So remember the trick to this. All you have to do is look here at each of the variable names. All you have to do is look at them. And for the null, what do you say between them? You say age group and political party, or you just say age group is independent. You could say R afterwards, but I just put independent usually between them. Age group is independent of political party. That's it. That's all you have to do. And then what's the opposite of independent? You just say age group is not independent. Exactly, not independent. So when we write the null and alternative right here, all you have to do for your null and alternative is write HO age group is independent. And then for the alternative, you can write age group is not independent. And that's simply it right there. That's all you have to write. There is just so few words between these. All you're saying, it's independent of it, it's not independent. And that means age group would tell you nothing about someone's political party. If they're independent, it means, I don't know, like, what if I said, you passing the test is independent of coming to class? Would coming to class be important to you? Passing the test is independent. No, it wouldn't be. You would think that passing the test would be dependent, which is not independent. You could say that too, that's fine. Some people like saying not independent, more classically independent, not independent. But not independent means dependent. And we understand that. Passing the class is dependent on going to class. And that's what we're doing right here. So think about it. Did you pass the class? That's yes, no, categorical. Did you go to class? That's yes, no, that's categorical. So we have categorical with that. So here we are with really what I love. And I wish I could draw on the screen today. But what we have right here is a expected cell missing. How do I know it's an expected? Because everything in position 2 is an expected. Every one of these numbers I'm highlighting is an expected cell count because it's in position 2. Watch out, because depending on the output, it can be different things. So you're given expected cell counts here, and you're missing A. So what is the formula for expected cell count? It's row total times column total or grand total, but let's go right here. And the reason I wish I could draw on the screen is because you can write the formula on the screen. What I do is I circle this number, and I do this in the video, and then I circle this number. This is the column total, this is the row total. What will you do with those two numbers? You will multiply those numbers and then put a division over them and divide by this number, which is the grand total. So please write on your test. Please write on your test. Because the row total right here is 391. The column total is 667. And do you see why it is? Independent lines up with this. And then this also lines up right here. So whatever lines up is the ones you use. And then you do over the grand total right here. So row total times column total over grand total, let's look at the math. 667 times 391 over 1602 equals 162.794. That is the expected cell count. Now you can do a double check here, because all of these expected cell counts, 140, 162, and 88, must equal up to what? This is your double check to make sure you got it right. They must add up to what? Double check here. What would they all add up to? They must all add up to the row total. Does that make sense? Because these all would add up to that number. They can't add up to something different. So let's add up 140 onto our number. And then let's add on 88.1092. And we get, just due to some decimal differences, 391. And it's so weird that the decimal differences happen. It's because it's rounding these numbers. So we're good to a few decimals. And if that happens on the test, don't freak out. It's just because we don't have all the decimals reported. So obviously there was a little bit of change left off in the number configuration. But you could also check it by adding up the expecteds for each of these, and they would have to add up to 667. So the expecteds add up to the totals in their respective row or respective column. So that's a good double check, and you could have solved it that way too, but more traditionally, this is the formula. Now the cell chi-squared is a measure of how odd something is. Which of these cells is the most odd from the observed, which is the count, and the expected? Which cell? If this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which cell is the most odd? And just look at the cell chi-squared. Cell 3 is really odd, I agree. That is the third most odd, because this one's really odd too. It's this one right here. This is like your friend telling you they'll pay you $168 and they only give you $113. Would that be a big problem? Would that be really bad? They say, I'll give you $168. You expect $168 and you only get $113. Oh, yes. But what about if your friends said they would give you $139 and they give you $141? Is that a big difference? Not really, right? And look at it, it's all good. And actually, they give you more in this instance. But the difference there is very small, and that's what the cell chi-squared is doing, is it's taking the observed minus the expected squared over the expected. And let's go ahead and grab that formula and put it side by side with us right here. So there's our cell chi-squared. So we're just going to grab the formula right here and go back up to our results and put it in beside us so we can see it at the same time. So our cell chi-squared right here is observed minus expected squared over expected. And it just tells us how odd the cell is. So if I take observed minus expected, and it doesn't matter which order you do it in because we are then taking this difference and squaring it. So when we square the difference, negatives become positives, but we do need to divide by the expected. If you don't divide by the expected, you get the wrong answer. And 2.054. That is the cell chi-squared. That is a measure of how odd that cell is. And if you look, you could compare, this one's about 15 off and ours is a little bit more off, but these are similar. You see our cell chi-squared is similar to this one. It's similar to these. Those are off by ish about the same amount. Can I write what out in words? Explain just deeper. The cell chi-squared is a measure of how odd the cell is. And you don't specifically need to know that, but I think it helps with the understanding of why we're computing this. The cell chi-squared is just a measure of how odd it is. Oh, the numbers I plugged in. Sure, let's do that. The numbers I plugged in were 162 minus 144,754. I then took and quantity squared that, and then everything was divided by 144,754. So there is the formula right here. That is the formula. There we go. And that is it. And that equals to, so it is observed minus expected squared over expected, and it tells you how odd the cell is. And I think we get into that, I won't mention that in a moment because it comes up here in a moment. As with any statistical technique, there are conditions that must be met. Let's check our first condition. Condition 1, what is condition 1? There's only a few people online, so I'll tell you, yes, random. And it needs to say we randomly selected them. Condition 2, easy to write this one out, 10%, which means we need to sample less than 10% of all people. These are people in political party. So I think we meet that one because we sampled less than 10%. Nice job, Brooke. And then condition 3, be careful because anytime you get to a third or fourth condition, you have to stop and think. We are in chapter 22, and actually this is the condition we're talking about right here. One of the conditions has something to do with there being enough data for it to be valid. And this condition is the expected cell count condition. Now, I like to remember this one this way. We have 2 categorical variables. We used to have the success failure condition where it was 10, but with 2 categorical variables, we're going to divide it in half and have 5. We want each expected cell count to be larger than 5. And you can look and see that all of the expected cell counts are larger than 5. But if we wanted to check this, if we didn't have the answers, what cell could we check? The one that has the what expected cell count? The smallest, the lowest, exactly. And that would be the one right here, and if I'm not mistaken, right here. Do you see how these are the smallest row and the smallest columns? Nice answers. Smallest row and smallest columns, as long as I'm not mistaken. And so this, as we would think, has the smallest expected. So if you had to compute the smallest, you could, and you would find that answer there by doing row total times column total over grand total. And the smallest expected passes, if the smallest is greater than 5, all others are greater than 5. So we are good. We are good to go. All expected cell counts are at least 5. So we're good. 87 is the smallest, it's greater than 5, and that's how I would answer it. I would say 87 is the smallest expected cell count, it's greater than 5, all others are greater than 5. Or you could say, I looked and all expected cell counts are greater than 5. Calculate the degrees of freedom. One of my favorite questions is degrees of freedom. What you need to do, and this is very specific because people mess this up, is you need to look at how many levels are in age group. Yes, Mallory, good. Let's go back to this. This only asks about the third condition, but there is the fourth condition, which is count data. And I'm trying to remember if I mentioned that at the start, but the question could be different on the actual test. The question on the test could be, what are the 4 conditions? So we said random, 10%, and we also said expected. But it could say, what are all 4 conditions? If it wanted the 4th, it would be count data. And how do we know this is count data? How do we know it's count data? We know it's count data because both variables are what? Both variables are categorical. Since both variables are categorical, the count data condition is met. So we will have count data when both variables are categorical. And that's how you would check that final condition. It's like, we could phrase it like, a certain condition for this test requires that the data be a certain type. What condition is this and is it passed? And you would say, The condition requires that it is categorical data, it is the count data condition, it is passed. So to have count data, you must have categorical data, and we passed. Lots of ways to ask the questions, and we're just trying to come up with anything we could think of to get it right for the test. So, good question right there. Nice job. Mallory and, Brooke, I was going to say ask all the questions you have, because you guys, a lot of people will watch this in the future, and they'll be like, I'm glad they asked those questions. Or they'll be like, why didn't they ask this question? You say, well, the other people should have showed up to class. We're doing this on a study day for those who are watching this in the future. So the question we just got to was, what is the degrees of freedom? The degrees of freedom will be the rows minus 1 times the columns minus 1. But the mistake people make is they use the total as a row and they use the total as a column, or row and column in reverse. When you do rows minus 1, you are looking at how many levels there are. How many rows are in this? I've highlighted them so you can see. How many rows are there? 4. How many columns are there? 3. So all I do when I solve this is I say 4 times 3, turn that into 3 times 2. Just drop each one of them by 1. And 3 times 2 equals 6. This is the degrees of freedom. You are correct. The degrees of freedom for the chi-square test of independence is rows minus 1 times columns minus 1. But don't even use the formula. Just remember, you're literally talking about the inner square of this. Do you see how what I've highlighted is six boxes? I've deleted 1 row and I've deleted 1 column, which leaves 6 right there. So there are 6 degrees of freedom. And that's very important to know what chi-square distribution you're using. We'll be using the chi-square distribution with 6 degrees of freedom. So that's got that. Good stuff right there. And so that would be in here. This is a chi-squared with 6 degrees of freedom. And below is the output, blah, 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 blah. Using an alpha 0.05, an important thing we need to know, our p-value is in the what right here? Our p-value is with the Pearson. That's just pure memorization, but it's the test we're specifically doing. We're doing the Pearson chi-squared test of independence. So just knowing which one we're doing is important. Truthfully, they're both very similar. I don't even have a good reason to tell you why to use the Pearson, other than it is the formula we are doing by adding them all up. And what you should know is that this chi-squared right here is actually the sum of all the cell chi-squareds. So you're actually doing the wrong one if you look at this right here. You have not obtained that chi-squared test statistic with the likelihood ratio. That's a different type of test, similar, and like I said, they're both very similar. So if you're watching this in the future and you're like, oh, I'm doing this for something else, they're both going to give kind of analogous results and have different reasons for usage. But when you add up, let's look at it again. When you add up all these cell chi-squareds, if I were to add up all these numbers, tell me, and you can abbreviate, if I add up all those cell chi-squareds, what number would I get if I add up all those cell chi-squareds? What would I get? I'd get the chi-squared, but which chi-squared? I add up all the cell chi-squareds, what would I get? It's a number on the screen right now. No, not the expecteds. If I add up all the cell chi-squareds, I get the chi-squared test statistic, which is 76.43. So all the cell chi-squareds add up to the chi-squared test statistic. And that's specifically why we're using the Pearson. All of these numbers right here, if you add them up, you will get 76.43. Does that make sense? So you could check your answer to B if you have time on the test by adding up all the other cells and then seeing, well, you could just add up your answer with B, or you could just subtract from the number. Does that make sense that all of them add up? So B has to be what is remaining if you don't get to 76.43. So you could check that answer too. It's a double check on that. If you have time, and a lot of people have time on the final, just double check that. And if it checks out, then you're like, well, yeah, I got it right. But it's a lot longer to add up all those than it is to just do observed minus expected squared, but it's a last double check. So, I mean, all the cell chi-squareds have to add up. And it also shows, you know, the theory there that this Pearson chi-squared test statistic is obtained by adding up all the cell chi-squareds. To obtain, and I just want to show this theoretically, what we need to do, so let's go over to statdistributions.com, great website. and we might be using our future website, I hope we are. We had a chi-square with 6 degrees of freedom. Our chi-squared statistic was 76.43, and our p-value is 0. This is a ridiculously large chi-squared test statistic, and as you can tell, the probability of our results or results more extreme happening due to random chance variation, given that the null is true, is very, 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 very tiny, as also shown in the jump output. Our p-value is less than that. So what would you do here with the low p-value? When the p is low, reject the null. So we are definitely going to reject the null hypothesis right here, definitely. And to put this in context, state the remainder in context, this is where a lot of people make mistakes. A lot of people make mistakes on this part. But just go back to your null and alternative. HO. I can go back in time here. Look at this. We're so close. There it is. I forgot I can go back in time. Age group is independent of political party. I reject that age group is independent of political party. I have evidence. That's it. That's all I had to do. I reject that age group is independent of political party. I have evidence that age group is not independent of political party. If you wanted to give a little more context, you could say, it appears that someone's age group tells us something about the political party. But this right here should be enough to make it make sense. And frankly, that's all you're doing. That's in context of the problem. That's good enough. I reject the age group is independent of political party. I have evidence that there is a dependency between the two. That's context of the problem. You don't just want to say I reject the null. You want to tell someone like, yeah, it looks like there is some sort of relationship between the two because they're not independent. So that is good enough. But what kind of relationship are we talking about? This is the key here. Well, you told me about the relationship, but now tell me about the relationship. And take a look at this right here. Who is shrinking as time goes on? As time goes on, which group is shrinking? The independents, probably typing it right now. The independents in the middle are shrinking. As people get older, they become less independent. And where are those independents going? And this is just, I don't know if this is real data, but they like it online. But this is just the data we have. This is just the trends in the data. It doesn't mean it's true. It doesn't mean anything about anyone. But it's something that generally you see that older people are more conservative and younger people are more liberal. And also we see, and especially we just went through the 2016 election. I don't know, maybe you're watching this in 2050. Hover cars yet? I hope there's hover cars. But in the 2016 election, a lot of younger voters voted for Jill Stein and Gary Johnson. So you see a larger portion of this young age group right here going to the independent. And as people get older, there's less people voting for independents. And I highly, highly doubt that this many would vote independent anyways. They got something respectively like 3 and 1% around there nationally. So now we get to a little bit of a harder question right here, wanting the percentages of the people who reported they were independent for each of these. So now listen how I say this. Given someone is 18 to 29, given someone is 18 to 29, what is the probability they're independent? How many people were 18 to 29? How many people were 18 to 29? So it's in the output right here. The amount of people who were 18 to 29 was 391. And the amount of people of them who were independent was 209. So 209 divided by 391. And you should see something here close to 53%. Does that look like it could be a little bit more than half? Does that look like it's a little bit more than half of it? I would say so. It does to me. Looks to be about 53%. And you should get smaller percentages as you go on. It's going to be hard to keep it on the screen. But all of these are just going to be, given that someone is 30 to 49, what is the probability they are independent? So 200 of these 419 people. Next, given someone is 50 to 64. So 145, that's just the counts right here. 145 of this 388 people. And then last but not least, and if you'll notice the percentage is going down, 113 of these 404 people. And that should be about 28%. And that looks to be about 28%. I'd say that looks pretty good there. And if you notice, it's going down each time. So this is important right here. Given someone is 65, out of all these people right here, what's the probability they're independent? So you have to look at all the 65-year-olds, and then you have to figure out 113 were independent out of 404. And that's got it right there. And I already did this one by accident just a moment ago. It says summarize the nature of the relationship. We see that people are less likely to be independent as they go older because the percentage went down from 53 to 28%, just rounding it right there. And we see that many of these people are becoming Republicans. The Democrats are growing too. The Democrats, wow, we reversed the colors here. It's interesting. The Democrats are slightly growing, but the numbers are more analogous because at the end, because the Republicans grow more than the Democrats, the independents are becoming more Republicans than they are Democrats. That's about as in-depth as we could answer that. So the nature of the relationship is there are fewer independents as people get older, and the independents are becoming more Republican than Democrats, but the Democrats are also growing too. Both Democrats and Republicans increase, and independents go down. So that's got it for that. Now we're on to the part where we're reviewing all of our old material. So the question here is, does studying really pay off? The answer is yes, I hope so. But does studying pay off? Is there a relationship between the total minutes you study and the average score that you achieve or other people achieve on the exam? The total time you study is a what variable. And just enter the first letter and I'll know what you're talking about. It's a what variable. It's quantitative. Nice job. And the grade you get on an exam is what? So maybe you already answered because the answer is also quantitative. So when you think about quantitative, you're thinking about regression. QQ, straighten up. No outliers, plot doesn't thicken. So we could make a scatter plot here. That's just an XY axis talking about the relationship between the increase or maybe decrease in your grade as you study more. So we can talk about, is there a linear relationship here? And this is a quantitative relationship going on. Nice job, Brooke and Mallory. A box plot. If I were to write a question that the answer were to be a box plot, so just to be specific, the answer was simple linear regression because it's quantitative data. If it said a scatter plot on here, that could also be the right answer, but we wouldn't want to include both because they're both goodish answers, but simple linear regression is the best answer. A box plot is for univariate quantitative data. So if we had univariate quantitative data like is somebody an outlier in how fast they can run a mile? Create a visualization to examine this. A box plot could be the answer to that question because how fast you run a mile is quantitative, and a box plot is a univariate quantitative visualization. Also, we could have, for what else for that? Feel free to write them in the comments while I say some. We could have a histogram, which is just a bins, and so histogram. I'll explain in 1 second. So I'll explain right now. Univariate means one variable. So box plots are univariate, just means one, correct? And where scatter plot is bivariate, it has two variables. So univariate displays of quantitative data include box plots. My brain's just breaking down today. Box plots, histograms are the top ones. Dot plots, stem and leaf plots, and there's a few others, but I won't mention them. You can also use pivot tables and pivot charts for those. But mainly box plots, histograms, and stem and leaves are kind of our big three. I don't know if I'm forgetting anything else. Anyone else feel free to mention it. I'm just spitballing off the top of my head. Univariate quantitative data. Univariate quantitative data. Hypothesis test for a mean could be a question like, your friend tells you that they can run a mile in less than 6 minutes. You want to see if there is evidence of this, so you ask them to run a mile 10 different times over the course of a month to see if they truly have an average mile running time of less than 6 minutes. And so what you're doing is you're testing their true average mile time. And so this is testing a mean right here. A decision tree question is a bit of a fun one because what we need to do in decision trees is generally have a lot of X variables. If we have a lot of X variables, we could ask something like, Kroger is doing an analysis to see if people will buy from their store. They have 50 different variables collected on their customers, and they want to understand the probability of somebody buying from their store, like becoming a new customer or something like that. So if you notice here, they have a lot of data, they have a lot of X variables, and they want to use that to make some sort of X or Y prediction. Decision trees can handle both quantitative and categorical data as both X's and Y's. Decision trees can handle everything, but we don't like them to handle indicator variables, identifier variables, excuse me. Teaching multiple classes and my brain jumps. We don't like for them to handle identifiers. So identifiers are something we generally don't put in them. They can use them, but don't do it. It makes bad trees. So decision trees are when you have lots of data and you want to analyze and kind of figure out the relationships. This is on our test, but we'll explain it right here. Your friend tells you that they can run the mile faster than you on average. So both you and your friend run a mile 10 times over the course of a month and try to see if there is a difference between your mile times. So you create a confidence interval to estimate the true difference between your average mile running times. And if you notice here, we have a sample of your mile times and a sample of your friend's mile times. So this is a confidence interval between the difference between your mile time and their mile time to figure out the true difference between your mile times. So it's a confidence interval to figure out the true difference between two population means. And then there's our right answer for two quantitative variables. Both variables must be quantitative for this. Any questions, feel free to ask. I know I kind of blurred through those, but there's so many ways to ask these. It's just a review of what you've learned and knowing what to use when. It's just, that's a big important thing to us, is that you at least know what to use in the future. You are the regional manager of 5 large grocery stores. You let the manager of each of these 5 stores make their own decisions who they hire. Since these 5 stores are within 50 miles of each other, you would expect the ethnic backgrounds of the employees at these 5 stores to be very similar. Is that the case? These are very close stores, and you want to see if the store has a relationship to the ethnicity of the people they're hiring. So what questions are we asking here? We'd have to ask someone, what store were you hired at? What kind of answer is that? You can write there, nice, I love it. It is C, it is categorical. And then we have to say, what is your ethnicity? And that is what? That is categorical. And then the answer is, what is the answer here? The answer, since it's categorical, is answer B. It is the chi-squared test of independence because we have categorical data. If it's quantitative, we can do simple linear regression. So that's already been reviewed. Also, Pearson correlation coefficient is for quantitative because that's scatter plots. All of these things are slightly related. Correlation is related to scatter plots, which is related to linear regression. So if you want to group those all up in your head, those are all similar. And frankly, this is maybe just a trick, but I think, see, I'd hate to, so I'll say it again. Correlation, scatter plots, and regression are all related. Correlation, scatter plots, and regression are all related because you make a scatter plot to look at the linear regression, and the scatter plots also look at correlation. So those are all related. So frankly, by the virtue of simple linear regression and correlation being on here, I would doubt one of those would be the right answer because they're very similar, unless it said something like we want to write an equation. If you want to write an equation of a line, you're looking at simple linear regression. Correlation will not get you the equation of a line. Correlation would just talk about the strength, direction, and form of, in this instance, Pearson correlation, a linear correlation. There's other stuff for other days, but Pearson's correlation would be the strength, direction, and form of a quantitative relationship. So I'll say it again. Pearson's correlation coefficient would be the strength, direction, and form of a quantitative relationship. Pearson's correlation coefficient would be the strength, direction, and form of a quantitative relationship. Simple linear regression would be to examine the quantitative relationship, and explicitly we could write a line or do other stuff, and that's why we used it before, because that was the only quantitative. A histogram, as mentioned before, is for univariate quantitative data. It would have to say something like, you want to see if your friend did really well on their chemistry test. They made a 75. So examine the scores in the class. And frankly, they might have done really well because we could examine the histogram, which basically looks like this. It's got bins, and we could examine the histogram to see where they landed on it because it's a visualization of quantitative data. And what your score is univariate quantitative data, univariate meaning one variable. Hypothesis test for the mean, once again, same thing. You want to see if your friend can, I don't know, there's so many things you could measure. You want to see if your friend, I just think of so many crazy things. You want to see if your friend is doing better on practice tests than an 85. So you're collecting data on your friend and on practice tests, or let's do it like for an ACT. You want to see if you're scoring better than a 25 on the ACT. So that would be a hypothesis test for a mean, because you're only collecting data on one mean, your score for a test, and then you're seeing if it's greater than 25. So the null would be that the true mean of your test score is equal to 25. The alternative would be that the true mean is greater than 25. So you could run a test there and see if your scores are better than 25 on the test. So that's got that. Lots of review there, just seeing anything we could come up with. So here we are. Here we are with power. Power represents the probability that we correctly fail to reject a true null hypothesis. No, no, no. A powerful test will find results. The power of the test is our ability to reject the null hypothesis. So a powerful test is able to reject the null. So a powerful test is one that allows us to correctly reject the null. So just as pure definition as it gets, power is the ability to correctly reject the null hypothesis. And we want to, so if you just remove right here, power represents the probability that we correctly reject, so just remove that. This would be true if you remove this, but the answer to this is false. This is false because it's that we correctly reject. If, based on the same data set, you change the level of confidence from 90% to 95, the resulting 95% confidence interval is less precise. And what we mean by precise is, like, think about your friend showing up and to a party, and they say, I'll be at the party between 7 and 8. And if you said, be more precise, what would happen to the interval? If you said, could you be more precise? The interval would get what? Smaller. And that's exactly it. If you said, be more precise, so the interval will get smaller. But if we go from 90 to 95, and I kind of phrased it weird, so going from 90 to 95, is the 95 less precise? If we go from 90 to 95, is it less precise? 90, 95, because 68, 95, so 90, 95, it is less precise. So that is true. So we have less precise right here. That is true. Please tell me if I make any mistakes. A less or more or something could get, how Mallory are you asking? So less precise. So think about your friend with the party. If they say, I'm going to be there between 7 and 8, and you say, be more precise. Or if you said, be less precise, let's say you said, be less precise. They say, between 6 and 9. So that makes sense that they're being less precise there. If you say 7 to 8 and then they say 6 to 9, that's less precise. Is that true? 7 to 8, 6 to 9, 6 to 9 is less precise? So if we go from 90 to 95, that is less precise, because 68, 95, 99.7. When you go out, you're just making it wider, which is making it less precise. So I'm holding on, just explaining further while a question is written. So as you go out 68, 95, 99.7, it gets less and less precise, because a precise interval is a very tight one. It's more confident, less precise. And that's kind of an inverse relationship. When you're more confident, you're less precise. So I'd say, I'm confident my friend's going to show up between 5 to 10, but that's a very, very not precise interval. It's less precise. I'm more confident, but less precise. Since 10% is more than 5%, how would 95 not be more precise? You're kind of creating a hypothesis test with it. So this one only wants to know about the interval, not a hypothesis test. Because if you want to talk about alpha here, this kind of switches the question. If you were to talk about alpha, this test would be less powerful. Because what you're doing by taking 10 and 5 is you're finding the associated alpha level of the two-tailed test, and the power of the test would go down. It's a different type of question. But only think about the question this way when we think about less precise. Precise means an interval that is what? Wide or tight? So a precise interval would be an interval that is wide or tight? Tight. So if I go from 90 to 95, does my interval get wider or tighter? From 90 to 95, the interval will get wider. It will get, if I go from 90 to 95, the interval will get bigger. And so that's less precise. And that's all that is. If you do the 5, 10%, you're thinking of how, yes, that's it. So you're thinking of how a confidence interval relates to a test, which is a whole different type of question. The power of this test will have gone down because the alpha will have gone down. So we could have written, going from 90 to 95, the associated test will have will be less powerful. And that is true. The associated test for the 95 is less powerful than the 90 because of the 10 to 5 alpha. Alpha dropped. But that's a totally different question. But good things there. So this one was true. It is less precise for those wondering. A p-value represents the probability of seeing the results you saw or results more unusual than that, assuming the null hypothesis is true. That is true. P-value represents the probability of our results or results more extreme happening due to random chance variation, given that the null is true. You can read that as a true statement, and that is something you should know right here. The only way to decrease the probability of a type 2 error is to increase the probability of a type 1 error. And this is something we were just reviewing a second ago. A type 1 error is directly connected to what? You can type one letter here, and I'll know what you're talking about. A type 1 error is directly connected to what? Alpha. Type 1 is directly connected to alpha. Alpha is the point at which we reject. So if we put alpha to 1, how much % of the time will we reject? If alpha's at 1, we will reject 100% of the time. 100% of the time. Now, to make a type 2 error, we have to fail to reject, which we can't make a type 2 error if we're just rejecting everything. A type 2 error is when you fail to reject the null when you should. The null is false, for those who learned that in my class. The null is actually false, but you did not reject it. So if we reject everything, we can't make a type 2 error. So this is slightly true. Increasing type 1, increasing alpha, does lower type 2. But we could also do what? How could we get a better, more powerful test? We could increase our what? You can type one letter here too. We could simply increase our n. Exactly. We could increase our sample size, so this is false. Because another way to make your test more powerful and have less type 2 error is to increase your sample size. Increasing sample size decreases beta, and the formula for power is 1 minus beta. So when beta is smaller, power is larger. In the business analytics presentation, we talked about how Target used data to determine if a customer was loyal and can continue shopping there. That is false. In the business analytics presentation, we talked about how Target figured out that a teenage girl was pregnant. That's what we talked about. Stephen Colbert does a really great segment on this. Look up Stephen Colbert, Surrender to a Buyer Power, and you can watch that segment if you haven't. I promise it's worth the 7-8 minutes of your time just to get some good laughs. And we often use something like this on the business analytics presentation. But there's other things that could talk about. We talked about Moneyball. It's Surrender to a Buyer Power. You can watch that if you want. It's a fun segment. It's really good. He makes a lot of good jokes. But I use that in the business analytics presentation to just show off business analytics. We talked about Moneyball and how the Oakland A's, I believe it was, we don't try to get that specific. It's like, what baseball team? We don't want to get that specific. But we talked about Moneyball and how the Oakland A's made decisions on who to recruit based on business analytics, and they actually did really, 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 really well. They have one of the longest winning streaks in baseball, and they did it with a very low salary. It wasn't due to chance. It was due to their data-driven decisions. So that has it. If you have any more questions, we'll wrap up here. But if you have any more questions, we got through the whole thing. I will be posting these to YouTube, which you're probably watching it on right now in the future.